So I'll give you a little introduction to concrete mixtures, parameters, and scenarios that we came up with for this. This is so anyway, we had three mixes we're talking about that I had information on all three tests. You can see one was a control mix that we did, and an 8% silica fume mix, and we had another one with a hyoclastic clastite pozzolan, which is a naturally occurring pozzolan. It's found in places like Utah and Iceland, and it's fairly reactive. So we're looking at all three of these and seeing how they behave, because we had tested that on all of them. So you can see, you can look at the binder types. This is typical type 1-2 cement. Realizing now we're moving towards 1L cements throughout the world, so this might be the last time, in the last few times we'll see a type 1-2 all by itself in something. But basically, we've and others have done works with 1Ls, and things work pretty much the same way. You can see the cement composition. The silica fume was a fairly pure silica fume, 94%. Typical stuff, and you can see the hyoclastic pozzolan was, it looked pretty much like it meets the requirements of natural pozzolan under the ASTM standard for pozzolans and fly ash, and you can see it looks very similar to a fly ash in composition. The test results, what we had, for this we have we did 642, which is volume of permeable voids. You can see they're all fairly similar at 90 days, based on, they all had similar water cementitious ratios, so that's not necessarily a big surprise. You can see the apparent diffusion coefficients is ASTM C1556. You can see that, as expected, the control had a higher value, and the silica fume had a low value initially, and you can see the pozzolan was in between, which is typically what one would get. The initial absorptions are pretty close to each other, with maybe a little bit better for the silica fume, the capillary absorption. The bulk electrical conductivity, which can be used. This was an old test, 1760. I guess there's now 1786, I believe, or 1876, which has replaced it. However, they both measured the conductivity of the concrete, and the idea is to look at conductivity coming down in time, or resistivity going up in time, and from that you can get some idea as to aging factor of the concrete. So this data was provided to all the people. On some of these, we had data going out past 5 years. NT build 492. That's what's used in the Duracrete model, and it's in fib, and non-steady state migration coefficients there. And you can see these numbers are different than the 1556 numbers. They're a little bit higher, but then they're an instantaneous number at 28 days, whereas the fusion coefficient is a 35-day average between 28 and 63 days when you run the test or so. So it's you're supposed to, ideally, you're supposed to take the diffusion coefficients measured at 1556 and adjust them for 28-day value. So, but basically they have the same trends. Stadium values, once again, we had 28-day, and this was the ionic diffusion coefficient. I will let Richard, who talks a little bit later, go into more definition of that, but that's, once again, an idea of how the ions are moving in the pore solution. It's done to hydroxide, but all these are ratioed out from hydroxide to chloride. So, and you can see that they get lower in time, pretty much in agreement with what's going on with the reduction in conductivity. And once again, they pretty much mirror the two other methods of measuring diffusion, which are the control the highest, the silica fume the lowest, and the pozzolan the next lowest. So what's interesting here is that over time, the pozzolan material is actually become lower than the silica fume. The stadium MTC, which is a moisture transport coefficient, and that's used if you have for non-saturated conditions to help on the modeling for stadium. And you can see once again that the highest values are under control, and they tend to come down for lowest for silica fume, and the pozzolan is the next lowest. But they're all coming down in time, which is of interest. Now, for modeling cases, we said, what are we going to model? So we could say everybody got the exact same thing to model. So, I mean, we said we're in Boston, so we're going to use Boston environment. We have a bridge deck, marine pile, marine wall. And we have you can see it here, the various thicknesses, 8-inch deck, 36-inch pile, and an 8-inch marine wall. And we have the icing salt, submerged, and splash. And we have an initial target life of 100 years. Okay, that's right in the middle of when you start getting into the monumental type bridges and or structures. And cover, typically 2.5, 3 inches. We have maximum surface concentrations that we set for everybody. Use the same thing. A black bar threshold of 735, but and enhanced initiation threshold. That is if you have some sort of corrosion enhancement, corrosion inhibitor, corrosion resistant bar, or something of that nature that would increase the threshold. We're not defining what it is, but from the point of view of modeling how much chloride it takes to go into initiation, that could mean that's just something that would increase the threshold value. So I think we don't have to define it. So this is useful for any materials that you know that for. We gave it a hydration time of 8 years. The Duracrete model and fib goes out to 100 years for the hydration and reduction time. Life 365, I think, stops typically at default value at 25 years. I think Sayan might end a little bit earlier. Our particular work shows that 8 years might be too much time for some things, and other things are coming down. I think Florida DOT is at 8 years, but we just to have everything on the same footing. We just said at 8 years hydration stops, so you stop your decrease in diffusion over time stops pretty much at the time of 8 years. Whatever it is there, that's it for going on. So in synopsis, we have various models available to model surface life for steel reinforced concrete structures, and you're going to see those after this. We have different test methods used to provide inputs for those models, and the results are going to be how they're used in the various models will be presented. The means of increasing chloride threshold values. Well, we just addressed that by just saying, I didn't get into a match saying what this product does versus that product. So I have a product that gets it to this threshold value, and you can and all these models, whichever you change the threshold value to, they can address that. We had 3 modeling cases for presenters to use. The emphasis today is on chloride-induced corrosion. So I mean, you have to. So that's where we're not looking at other things at this point. And at the end of session 2 today, we're going to have a panel discussion with the audience. So you'll be able to ask more questions than you might be able to ask after an individual speaker is finished. I think I've got plenty of time here. But so basically, this is how we set it up for everybody to look at it, and I can answer some general questions if anybody has anything at this point. Yes.
And Neal, thank you. Was there any consideration to the fact that when you're fixing these parameters the same across the models, you're altering the assumptions of each model? So for example, the FIB 100-year hydration, you're changing it to 8. Life now it's 25 to 8. Your chloride threshold is going to be different from the established assumptions. So I get that you want to have fixed parameters, but in itself that's also changing the defaults.
Yes and no, because all these models mean what you want to use are the boundary conditions. They're adjustable even in the model. I mean, FIB gives you a guideline to use these numbers for Duracrete, and Life 365 tells you here's a default thing. Yeah. So they're usually useful for people that are doing a quick look to see what's going on. As I would suggest, as a design engineer, you got to use some judgment. And some of these things, if I take some of these D values, for instance, of M value, and I go out to 100 years that this thing keeps decreasing, I've got stuff that has the permeability of a diamond.
Sure.
You know, or if you want to go out 1,000 years or something, you know, then so realistically, you know, things slow down. Okay, and we have data, and Florida and other guys have data showing that things really don't go out to 100 years or 25 years. Now, part of the problem is, since we have time, is that a lot of the information was discovered, and I think Jose touched upon it at our 365 meeting yesterday. A lot of the long-term data was concrete made at the turn of the last century, where the cement content was higher, the C3S values were much lower, the tricalcium silicate values were low, they had high dicalcium silicates. They tend to absorb more chloride and react over it. They don't absorb it, they react slower in time. So you could get continual hydration of your cement for years. They're coarser blends, blanes, so they're coarser cement, so they take longer to react. They also have they also have, because of the higher C2S, they take longer to react. So they're producing calcium hydroxide for years upon years. So what happened there is that you get an idea, there you might get ultimate strengths 10 years out. Now our cements are designed with high C3S values, lower C2S. They're much finer blane than the stuff that was out there, so they level off. If your strength's leveling off at, 28 days, so your strength, and you get to 90 days, you see no more strength development, where's your calcium hydroxide coming from? The hydration process has stopped. Your pozzolan that you add is not going to get better if it doesn't have any calcium hydroxide to react with it. It doesn't react with water, otherwise it would be a cementitious material. So basically, what happens is two things. You don't run out of hydration of the cement, and two, your water cementitious ratios are so small that you can't even get the water into other cement. So a lot of these things are also more applicable to higher water contents that would have been used. And if you look at, it'll come out, but some of these models are good between 0.40 and 0.60, where they had data, but it was data that was kind of old. So the model itself was a good model, but how long some of these things go on might be dependent, on the fact that we have different materials today than we had when the long-term data that went into the model. Okay, I hope that answers your question.
Yeah, I just think it would be also a good comparison to show same concrete and run it with its, those predetermined defaults and see how much they vary.
Yeah, we'll have a little bit of one of the paper selections later on will show how things change a little bit in time. Like the M value will change in time.
Thank you.
So, which is basically how fast it comes down. Good question.
Any other questions?